Hello and welcome back to SLO 6, 8, and 10. This is part 2. Again, we are going to determine the component form of a vector, express a vector in terms of the unit vectors I and j, and perform vector addition, subtraction, and scalar multiplication. Since this is part 2, the first two bullets have been covered, so this one's focusing on vector addition, subtraction, and scalar multiplication. So we are going to perform vector addition, subtraction, and scalar multiplication. Let's begin with vector addition. We're going to find the sum of vector c and d. Vector c is equal to 4i plus 6j, and d is equal to negative 9i plus 2j. So as you can see, c is this purple vector, and d is this red vector. So the interesting thing about this particular set of vectors is that c starts at the origin and has a terminal point here, while d starts from the tip of vector c. So using this, we could use the triangular method to visually represent the addition of these two vectors. But mathematically, we can do negative 9 plus 4 and 2 plus 6 because we're going to add the i's together and the j's together. So we'll have negative 9 plus 4i plus 2 plus 6j, and that will give us negative 5i plus 8j. But visually, if we look at the vector here, we kind of form a triangle based around these two vectors because the terminal point of vector c is the initial point for vector d. So knowing this, we can actually draw this green vector of negative 5i plus 8j here to represent the addition of c and d. So let's do some more vector addition with vector p and q. So vector p is this purple vector and vector q is the red one. As we can see, vector p is represented by 3i plus 4j, and vector q is negative 2i plus 2j. And adding these together mathematically, we'd have 3i plus negative 2i plus 4j plus 2j. So 3 plus negative 2 times I is 1i. We could just write I, but I'm showing that here. And 4 plus 2j, we have 6j. So the difference between this vector addition problem and the previous one is that vector q here does not start where vector p ends. So they share an initial point, meaning you can't use the triangular method here. You'll have to use something called the parallelogram method. So here's a visual representation of the parallelogram method of adding vectors. So again, since they share an initial point, you can't just draw a vector from here to here or here to here. What you'll have to do is start the vector at the convergence of these two vectors and then end it based on the distance that's created by a parallelogram. So it's kind of like you're putting vector p here and vector q here and drawing a parallelogram, and then you'll have this added vector, the resultant vector, to be between them. So it'll start at where they started and end at this point here. Let's get into vector subtraction. I will be using the same vectors from the previous example. So we have, again, vectors p and q, but we're subtracting q from p now. So basically, when you do vector subtraction, you're taking this vector here, q, and you're gonna point it in the opposite direction and then add it like normal. So think this dotted blue line is your new vector q, and then to add it, you would use the parallelogram method again. And then you would draw the resultant vector from the initial point here to the terminal point where these lines would converge. So here's two more vector addition and subtraction examples. We have vector A at 5, -6, and vector B with -2, 7. Adding these two vectors together, we have -2 plus 5 and 7 plus -6 to get A plus B. That's just 3, 1. And then for A minus B, we have 5 minus -2 and -6 minus 7. This gives us 7, -13. Let's get into scalar multiplication. We are given vector v at -2, 8. So recall that a scalar is just something that only has one value, so it's not a vector. In this case, our scalar is 1/2 because we're taking 1/2 of v. So we have vector v here, which starts at the origin and then goes up 8 and over to the left 2. If we're taking 1/2 of this vector, we just have to multiply each of these components by 1/2, and this will give us 1/2 times -2, which is -1, and 1/2 times 8, which is 4. This green vector here represents the when vector v is multiplied by a scalar. So we're going to now do vector addition with a scalar. So we have vectors s and t. S is -2, 3. T is 2, -1. And we're going to find the new vector x is equal to 3s plus 2t. Again, we have a scalar of 3 for vector s and a scalar of 2 for vector t. So let's multiply each of these vectors by their respective scalar. So 3s would be 3 times -2, -6, and 3 times 3, which is 9. And 2t, which is 2 times 2, which is 4, and 2 times -1 is -2. And then we're going to add these values together. So we have x equals 3s plus 2t. So we have -6 plus 4 and -2 plus 9. And this gives us -2, 7 for our resultant vector. So this is how it would look graphically. So again, since we are multiplying vector s by 3, we can draw that 3 times, and then vector t times 2, we can draw that twice. Since they start at the same point, then we have to use the parallelogram method. So just redraw these here and redraw this here, connect the two, and now you have the resultant vector. We're going to quickly look at one more example. We have vectors O, 4, 8, and vector P, -2, -1. We're going to find the new vector R, which is equal to 1/4 of O minus 2P. Doing this mathematically, we will have 1/4 times 4, which is 1, and 1/4 times 8, which is 2, and 2p, 2 times -2 is -4, 2 times -1 is -2. We'll subtract them now, so we have 1/4 O minus 2p, or 1 minus -4, and 2 minus -2. This gives us a resultant vector of 5, 4. Here's how it looks visually. So since we're taking 1/4 of O, we have to scale it down. And since we're doubling p, we have to scale it times 2. Since we're subtracting 2p from 1/4 of O, we draw it in the opposite direction, shown by these orange dotted lines here. And then we can use the parallelogram method once again to draw this out, draw this here, and then connect from the origin to the terminal point. Thanks for watching. Have a good day.